All right, let's get right into it. Welcome to the explainer that's going to totally transform your daunting grade 11 physics exam review into an empowering step-by-step playbook. Look, if you're gearing up for your SPH3U exam, you already know that Unit 1 on forces in motion. Yeah, that is the absolute foundation for literally everything else you're going to do. So today, we're locking down core classical mechanics together.
Here's exactly what we're covering today. 1. Kinematics versus dynamics. 2. The four common forces. 3. Mastering free body diagrams. 4. Tackling forces on inclines. 5. Solving connected mass systems. And finally, 6. Your exam problem-solving strategy.
Section 1. Kinematics versus dynamics. Setting the arena.
Okay, to really set the stage here, you kind of need to split your physics brain right down the middle. Over on the left side, we've got kinematics. Kinematics just asks two basic questions. Where is it, and how fast is it going? You're mostly using your trusty displacement, velocity, and time equations for this. But dynamics, over on the right, well, that is the real game. Dynamics asks, why is this thing moving in the first place, and what exactly caused it? It looks straight at the mass and the actual forces causing that motion. So our toolkit shifts gears from simple motion equations to free body diagrams and vector resolution.
But hey, do not toss out your kinematics knowledge just yet. Even though our main focus today is completely on dynamics and forces, those kinematic tools, like, finding velocity from position time graph, they're still going to pop up everywhere. You might actually need to find an object's acceleration from a velocity time graph before you can even begin calculating the net force acting on it. It's all totally interconnected.
Section 2. The four common forces. Meet the players.
So you're going to see these everyday contact forces constantly on your test papers. As you can see, we've got the force of gravity, the normal force, tension, friction, and applied force. Basically, these are the physical interactions happening all around us all the time. Think about the friction keeping you from completely wiping out on an icy Ottawa sidewalk, or the applied force of your hand shoving a heavy shopping cart through a Loblaws parking lot. In physics, all these everyday pushes and pulls are measured in newtons, and they are the immediate causes of any change in motion.
Now, let's zoom way out for a second to the macro perspective, because this is pretty wild. On a cosmic scale, physicists recognize that absolutely everything boils down to just these four fundamental forces. You've got the gravity holding our planets together, the electromagnetism powering your phone, right down to the strong nuclear force binding atoms and the weak force driving radioactive decay. You'll dive way deeper into those nuclear forces in grade 12 modern physics, but for right now, gravity and electromagnetism are your main focus. Fun fact, everyday forces like friction and the normal force we just talked about, they're actually just electromagnetic interactions happening at a microscopic level. Kind of mind-blowing, right?
Section 3. Mastering free body diagrams. The ultimate cheat code.
Listen up, because a free body diagram is not just some random doodle you sketch in the margins to get partial credit. It's a mathematical translation device. Here's how it works. You represent the object as a simple, humble box. Then you draw arrows radiating out from the exact center of that box. The length of the arrow reflects the true magnitude of the force, and the direction shows exactly where the force is acting. This right here is how you take a messy, confusing real-world word problem and translate it into a clean, totally solvable math equation.
But here's the catch, and it's a big one. The stakes for setting up your free body diagram correctly are incredibly high. Look at this quote. If you miss a single force arrow, say you just forget to include friction on a sliding object, it will completely derail all your math from that point forward. Your net force will be wrong, your acceleration will be wrong, your final velocity will be wrong, the whole shebang. Your FBD is your absolute rock-solid foundation.
Section 4. Tackling forces on inclines. Running the drills.
Okay, notice how the normal force, which is just the force of a surface pushing back against an object, acts on a perfectly flat table. It points straight up, directly opposing gravity. Simple enough, right? But look what happens the second we put that object on a ramp. The normal force acts entirely perpendicular to the inclined surface. It does not point straight up anymore. This single tiny detail is where so many students lose easy points on the exam.
And because of this tilt we just looked at, gravity is no longer perfectly lined up with your normal force. It's like gravity has a split personality on a ramp. You literally have to slice the force of gravity, your weight, into two separate components. First, you have the perpendicular force, which is your weight times the cosine of theta, and that perfectly balances out the normal force. Then you have the parallel force, which is weight times the sine of theta. That parallel component is the invisible hand actually dragging the object down the ramp.
Let's see how this actually plays out in a typical exam question. We've got a 60-kilogram skier on a 25-degree slope. First things first, we find that parallel gravity component that's making her slide downward. Now, if the snow is completely frictionless, her acceleration is purely driven by gravity pulling her down the incline. But if we add in 45 newtons of opposing friction, as you see in Part B, we have to apply Newton's second law. We simply subtract that friction from our parallel gravity component to find the exact net force. That spits out a newly reduced net acceleration of 3.39 meters per second squared. It's a rhythm. Draw the diagram, find the components, apply the law.
Section 5. Solving connected mass systems and tension. Let's pose a little puzzle. Imagine a 70-kilogram person standing perfectly still, right in the middle of a tightrope, and it sags just a tiny bit. How in the world do we calculate the invisible force, the tension, that's stopping them from hitting the ground?
Well, since our tightrope walker is entirely stationary, the net force in both the x and y directions has to be exactly zero. They aren't going anywhere. The horizontal forces pulling left and right perfectly cancel each other out, which mathematically proves that the tension on both sides of the rope has to be equal. Then, looking at the vertical components, the upward pull of the ropes, which we calculate using the sine of that tiny 5-degree angle, must perfectly equal the downward pull of the walker's gravity. By setting up this zero net force equation, we can completely isolate and solve for the massive tension required to support their weight.
Now here is a huge pro tip for when you inevitably face a test problem with connected objects. Imagine a 60-kilogram mass and a 40-kilogram mass tied together by a rope, being yanked across a frictionless floor by a 250-newton force. The absolute best secret here is to just treat both masses as a single, combined 100-kilogram mega-object first. Calculate the total acceleration of that entire system using Newton's second law. Once you have that overall acceleration, then, and only then, do you zoom back in on just one of the individual blocks to figure out the specific tension in that connecting rope. It is a total game changer.
Section 6. Your exam problem-solving strategy.
When you finally sit down for the test and you feel that exam panic trying to set in, I want you to blindly rely on this exact 5-step method for every single dynamics question. Step 1. Draw your free body diagram. Step 2. Choose your coordinate system and remember to tilt it if you're on an incline. Step 3. Resolve all those diagonal vectors into clean x and y components. Step 4. Apply Newton's second law, net force equals mass times acceleration, for each axis separately. And Step 5. Please, always check your units. Sticking to this structure guarantees you will never get lost in a sea of numbers.
And as you're working through those steps, constantly refer back to your visual. Let your initial free body diagram tell you whether your forces are balanced or unbalanced. If the arrows perfectly cancel out, boom, you instantly know you have a constant velocity or the object is totally at rest. If they don't cancel, you know for an absolute fact you have an active acceleration pointing in the exact direction of the larger arrow. Just let the diagram do the heavy lifting for your math.
So here we are at the end. You now have the exact playbook to deconstruct the hardest mechanics problems they can possibly throw at you on the SPH3U exam. You know kinematics from dynamics, you know your inclines, and you absolutely know how to handle tension. But honestly, it all comes down to your execution on test day. So my final question for you is this: will you put in the reps and practice drawing those diagrams enough to ensure you never miss a single arrow? Because as we've seen today, just one arrow changes everything. Get out there, start practicing, and good luck studying.